Well, good afternoon, everybody. Welcome. Good to see you. Today we're going to continue our study of exceptional control flow by looking at some higher level mechanisms known as Linux signals and C non-local jumps. Now, we're going to spend most of our time looking at signals because they have a lot of subtleties. The semantics can be kind of confusing. So we're going to spend most of our time there. And I'll mention the idea of non-local jumps, but for details on those, you'll want to look in your textbook and in the slides at the supplemental slides at the end of this slide deck. Now, to motivate the notion of signals, I want to talk a little bit about shell programs. Now, as we mentioned last time, there's only one way to create processes on a Linux system, and that's using the fork call. In fact, all of the processes on the system actually form a hierarchy. So the very first process created when you boot the system up is the init process, which has a process ID of 1. And then all other processes on the system are descendants of that init process. Now, the init process, when it starts up, it creates daemons, which are long-running programs that provide services typically. So, for example, a web server, other kinds of services that you always want running on the system. And then eventually it creates login, so-called login shells, which provide the command line interface to users. So when you log into a Linux system, what you eventually get to is a login shell that's expecting you to type commands. Now the login shells execute programs on your behalf. So when we type something into the shell, say we type the ls command, we're asking the shell to run the executable program called ls. And so what the shell will do is it will create a child, and then it will execute ls within that child process. And it's possible that that process may create other child processes. So a shell is an application program, no different from any other program, that executes programs on the behalf of users. Okay. The default shell for Linux is called bash, but there's other shells that were created earlier with earlier versions of Unix. SH was the original shell. It's called the Bourne shell because it was created by Stephen Bourne. And when Berkeley came out with their distribution of Unix, they created a shell called CSH. Now, the execution in a shell is a sequence of read and evaluate steps. So first, a shell prints out a prompt, and then it waits for you to type something in on the command line and hit return. Okay, and typically what you're typing in is a command, which is just so the first thing you type is a command, and then you follow that with optional arguments separated by spaces. Okay. So once you type in a command and those optional arguments and hit return, the shell checks for the end of file character, which is a control D to a terminal, and if so, it exits. Otherwise, it evaluates that command line. And the evaluation consists, and then when it returns from the evaluation, it just does the same thing over and over. Now, the evaluation consists of the following kinds of steps. First, it parses the command line, and in the process, so it takes the command line, which in this example is in buff, and it produces an argv array. Okay, where argv0 is a command, and then argv1 and 2 and so on are the optional arguments. And the convention in a shell is that if the command line is terminated by an ampersand, then you're asking the shell to run that command in the background, meaning the shell won't wait for that job to finish. before it goes through its next read step. If the line that you type doesn't have an ampersand, then you're asking the shell to run that job in the foreground, which means the shell will wait. So first we parse this, this command line into an argv array, and we return whether or not it was terminated by an ampersand. So BG for background. If argv0 is null, then that means we just hit return, right? So it's an empty line. So we'll just return and just ignore those. Now a shell also implements what are called built-in commands. So various things like jobs, BG, FG are examples of built-in commands which are just implemented in the shell itself. So if the first thing you type, if the command you enter is a built-in, then the shell will check that. It will check argv0 to see if it's a built-in command. And if it is, it'll just execute it, whatever it is you asked it to do. Okay, otherwise, if it's not a built-in, then that means that you're asking the shell to run some program. Okay. So in that case, the shell will fork a child, and then the child will execute that program by calling execve, passing as the first argument the name of the command, and as the second and third arguments argv and the environment, respectively. Now execve, if you recall from last time, never returns unless there's an error. So we check the return value for execve, and if it returns less than 0, in fact, the only time it'll return, if it does return, it'll always return -1. But we're just being careful here. So we check that for an error and print an error message if we find an error, and then exit. So once the parent gets control again, then it waits for that foreground job to terminate. Okay, so if it's not a background job, then it waits for it to terminate by calling waitpid and waiting for that foreground job to terminate and reaping it. Otherwise, if it's a background job, it just prints a message and goes on. So this is really interesting, right? That there's really the only difference between a foreground job and a background job is just that the shell does a waitpid on that job or not, right? So otherwise, there's really no difference. Now, what's the problem? There's a problem with our example shell. And the problem is that we're doing the right thing for the foreground job. We always have to reap these children so so that their state can be released. But we're not doing anything to reap any background jobs, right? If it's a background job, so if not BG, we're just printing a message and then we're returning, and then we're continuing with this read evaluate step, and never going back and taking care of that background job. So this is a problem because that background job will eventually become, if we have enough of those jobs, we create a memory leak that could crash the system, right? So this is an error. So what are we going to do about this? Well, it turns out that exceptional control flow will help us solve this problem. And what happens is that the kernel will notify the shell when any of its children terminate. Okay? And then the shell can then react to that and issue a waitpid. Okay? And this notification mechanism that the kernel uses is something called a signal. So a signal is a small message that the kernel delivers to a process to notify it that there's been some event in the system. Now, so this is very similar to the exceptions that we studied the last time, right? Except it's all implemented in software. Now, kernel signals are always sent from the kernel, but sometimes they're sent at the request of another process. right? Sometimes the kernel will notice that there's some event. Other times, another process will ask the kernel to send a message to some other process. Now, we say that it's a small message because the only information that's contained in a signal is its unique integer ID and the fact that it was delivered. Okay, so there's nothing else in a signal except that it arrived and that it has some unique ID. Now, examples of these are the SIGINT. So signals have this unique ID, and then they also have a name. So the SIGINT is what when you type Control-C on the command line, the kernel sends a SIGINT to any processes in the foreground. And the default action of receiving a SIGINT is to terminate. Right? So this is how, if you're running a foreground job, you hit Control-C, you get the prompt back because it kills that job. SIGKILL, number 9, can be used to terminate any program. So these two SIGINT and SIGKILL have the same effect on the programs. They kill the program. The unique aspect of SIGKILL is that there's no way to ignore it or override it. Okay, so this is like the fail-safe. As we'll see, there are ways to catch and ignore other signals like SIGINT. SIG-SEG-V is our favorite seg fault, segmentation violation. So if you access a region of memory that's protected or not legal, then your program the kernel will send that process a SIG-SEG-V, okay, signal, and the default effect of that is to terminate the program. SIG-alarm is a way within your program you can arrange for a signal to be sent to yourself. So you can say inside your program, send me a SIG-alarm signal in 3 seconds, something like that. So this is a way to do things like you can set up timers, you can set up timeouts. Like if you want to set a timeout value and you're doing some work and you want to guard against that work taking an exceptionally long time, you can use SIG-alarm to set a timeout. And then a very important one is, as we'll see, that will be very important for our shell, is the SIGCHILD signal, which the kernel sends to a parent every time one of its children terminates or stops. Okay. So this, as we'll see, now we'll see this is how our shell is going to actually reap all of its children, right? Is by taking advantage of the SIGCHILD signal. But before I can show you that, we need to go through a number of concepts around signals. Okay, like I said, the semantics of signals, it's probably one of the thorniest aspects of Linux. It was developed very early in the lifespan of Linux and it maybe wasn't as clean as it could be, right? So in order to get a handle on signals, we're going to have to be very careful about defining terms and very careful about the way we talk about them. So we say that the kernel sends or delivers a signal to some destination process, and it does this by setting some state in the context of the destination process. Now, nothing happens except that some bits get changed in the destination process context. Okay, there's no immediate impact of sending a signal. Right? Now, a kernel sends a signal either because it detected some event in the system, like a child process is terminated, for example, or another process has asked the kernel to deliver a signal on its behalf. And there's a number of ways to do that. One of them is with the kill system call. It's kind of an unfortunate term, isn't it? I mean, so kill is a general way to send signals, and the the impact is sometimes not to kill the program, right? But for some reason they chose to call it kill. Now, the destination process receives a signal when it's forced by the kernel to act in some way, to react in some way to the delivery of a signal. Okay. So these are two very different things. Sending a signal sets state in the context of the destination process. Receiving a signal is what happens when the destination process is finally forced by the kernel to act in some way, to react in some way. Now, some possible ways to react are to just ignore the signal, okay, to terminate the process, or to catch the signal by executing a user-level function called a signal handler. So in this case, when we catch signals, it's very similar to and execute a signal handler. It's very similar to executing an exception handler in response to some kind of event in the system. Now the difference is that exception handlers are in the kernel. Signal handlers are actually just in your C code. Okay, and they execute in your process. So the way to think about if we catch a signal by executing a signal handler, we have our process executing instructions, and then a signal is received by that process. So the kernel passes control to a signal handler, which is also just in the code that's executing in the current process. It's just a function in our C code. The signal handler runs, and when it returns, it eventually returns back to the next instruction, and then we continue. Okay? So it's just like kind of like an interrupt, right? We just temporarily pause what we're doing in our code to execute this handler before just continuing on. Okay, now we say that a signal is pending if it's been sent by the kernel but not yet received. Okay, so at any given point in time, there can only be one pending signal of any particular type. Okay? So this has very important consequences for using signals, because you can't queue signals up. Right? At any point in time, there can only be one pending sigchild signal, for example, or sigint signal. And if a subsequent sigchild signal, say, is sent, it just overwrites. Well, you can think of it as it has no impact. It's just discarded, right? If there's already a pending signal, so they don't queue up in any meaningful way. Now, a process can block the receipt of certain signals. Okay. Now, it can't stop signals from being delivered, but it can stop the process from having to react to that signal when it's received. Okay. So blocked signals can be delivered, but they won't be received until the signal's unblocked. And pending signals are received at most once. Okay. Now, the kernel keeps track of these pending and blocked signals in bit vectors that we'll call pending and blocked. And pending represents the set of pending signals, right, where each bit in the pending bit vector corresponds to some particular signal. Okay, so this is why they can't be queued, right, because there's only one bit for any signal k. There's only one bit in the bit vector, and when we deliver a signal, we'll set that bit. The kernel will set that bit. If we deliver another signal of the same type, it'll just set that bit again, which has no effect. Now the kernel sets the bit in pending when the signal's delivered, and it clears it when the signal's received. And the kernel also provides mechanism for users to block signals with this blocked bit vector. So the blocked bit vector is the same size as the pending bit vector. Turns out it's just a 32-bit int. Okay. And it can be set and cleared. The bits in that can be set and cleared using the sig proc mask system call. Okay, now the blocked, in the Linux literature, the blocked bit vector is also called the signal mask. Okay, now I want to look in a little more detail about sending and receiving signals. So let's start first with sending signals. First, we need to understand the idea of a process group. So every process belongs to exactly one process group. So here I'm showing a shell that's in process. It has a process ID of 10 and a process group ID of 10. The shell created a foreground job, which has a process ID of 20 and a process group ID of 20. And then all of the children that this foreground job created have the same process group ID of 20. So these process groups can be set by a system called set process group ID. And you can fetch that process group using the get process group system call. So you can see in this example what this shell has done is it created a foreground child. So it created this child, and it changed the process group ID to be equal to the process ID of the child. And then when this child created other children, they just inherited the same process group ID. Okay. Now this notion of a process group is useful because it allows you to send signals to groups of processes at the same time. And you can do that with a program called kill, which is typically in /bin directory. And the kill program, you can use the kill program to send an arbitrary signal to either an individual process or all the processes in one process group. So let's look at an example. This program, this forks program, creates two children, with each of which has a process group of 24817. Okay, and of course they have different process IDs. And so if we do a PS, we see these two processes running, and these just go into loop, so they'll just run continuously. Okay, now we can use kill to kill an individual process. For example, so if we call it, the first argument indicates what signal you want to send. So in this case, it's signal 9, which is the sig kill signal. So kill -9 is a very typical. Usually, if you want to kill processes, you just kill -9. And actually, one of my favorite Autolab nicknames for 213 was the nickname was kill -9 15213. So, but then the second argument is the process ID. So this is asking the kernel to kill process ID 24818 by sending it a sig kill signal. Now, if the process ID is preceded by a dash, then it sends a sig kill to every process in process group. Then it treats this argument as a process group, and then it sends a signal to every process in that process group. So in this case, it will send a sig kill to both of these children processes. And then afterwards, if we do a PS, we see that those processes are gone. Okay, that it really did work that way. Now, another way to send signals is by typing either Control-C or Control-Z to the command line. Control-C causes the kernel to send a SIGINT to every job in the foreground process group, and Control-Z causes it to send a sig tstop signal to every job in the foreground process group. The default action for SIGINT is to terminate the process. The default action for the sig tstop is to suspend the process, stop it, until it receives a sig CONT signal. So you can see an example of this. Here we have a program that creates a parent and a child running in the foreground. So the parent's running in the foreground. Now when we type Control-Z to the command line, the shell notifies us that it's suspended that process. And if we do a PS, we can see the parent and the child indeed are suspended. So the PS indicates that it's suspended or stopped using T. Now next we type in the built-in, the shell built-in, which is FG, and FG restores those suspended jobs to the foreground. So after typing FG, now we're running our program again in the foreground, and then we can kill it by typing Control-C, which elicits a SIGINT whose default action is to terminate. And then when we do a PS, we see that indeed that they're gone. Now the third way that we can send signals is by using the kill system call. Here's an example of how that works. So in this example, we're creating n children, each of which goes into an infinite loop, and we're recording the process ID of each child that we create. And then in another loop, we go through and we kill each of those child processes by using the kill function, passing it the process ID and the signal that we want sent to that process. Okay. And then we do our due diligence and reap each one of those children that we've terminated. Now, this isn't strictly necessary because we're going to exit. As soon as this fork12 function returns, we're going to exit the code. But we're just being careful here and maybe a little pedantic. But okay, now let's look at how a process receives signals. Now suppose process A is running along, executing its user code, and then there's a control passes into the kernel because of some exception. Now that exception can be either a timer going off, maybe an interrupt, or it can be a trap. User calls a system call. Okay, but it's always caused the trap into the transferring control into the kernel is always caused by some exception. So at this point, the kernel calls its scheduler function, and it decides to do a context switch from process A to process B. And it gets process B all set up, and right before it returns from that exception, and right before it's ready to pass control back to the user code in process B, it checks for any signals any pending signals. Okay. And it does this by computing a bit vector PNB, so pending non-blocked, which is the logical AND of the pending bit vector and the inverse of the blocked bit vector. Okay. So PNB is a list of all the pending signals that aren't blocked. Okay, so these are all the pending signals that should be received. Now if PNB is all zeros, then there's no pending signals, so it just returns, it passes control back to process B, which can continue executing. However, if PNB is non-zero, then it chooses the smallest non-zero bit in PNB, and it forces process P to receive that signal, the corresponding signal. The receipt of the signal triggers some action in the process. And then we repeat that for all the non-zero signals K, or non-zero bits that are set in PNB. And finally, when we've gone through all the non-zero bits, then we pass control to the next instruction in the in process P. So the receipt of a signal always triggers some action, which is either the process terminates, the process stops until it's restarted by a sigcont signal, the process ignores the signal. Okay, so there's always some predefined default action. But we can modify that default action by using a system call called signal. Okay, so we can, now signal's that's another sort of misleading kind of term, just like kill, right? Because when we send a signal to a process, we don't always want to kill it. And signal doesn't actually signal anything. It just modifies the default action associated with some signal. Okay, so if the signal function takes a signal number and then specifies a change in the default action for that signal. And those default actions can be either to ignore the signal, okay, ignore signals of type signum, revert to the default behavior for that signal, or we can give it, or it can be the address of a user-level signal handler, which is a function that we've declared in our C program. Okay, there's nothing special about the function. It has a certain prototype. It takes a single argument, which is the signal number. So when that function gets called in response to receiving a signal, that argument will be set to the signal number. Okay. So calling signal and specifying a signal handler is called installing a handler. And then executing the handler is referred to as catching or executing or handling the signal. And this handler then is just like an exception handler. When it returns, when it's executed, it will interrupt whatever is currently executing in the process. And when it returns, it'll return back to that point and continue executing. Okay, so here's a simple example of installing a handler. So here in main, we're going to install a sigint handler, which is called sigint underscore handler, which is defined up here. And the prototype for this function is returns nothing, and it takes a single integer argument, which is the signal number, and returns nothing. Okay. And after we install that handler, then we're going to execute the pause syscall, which just waits for a signal handler to execute. Okay, so pause terminates the current, or suspends the current process until a signal is received and a handler executes in that process. And then pause returns. So we're going to wait until a sigint happens. So sigint, recall, is when we type Control-C. So when you were doing your bombs, did you panic at some point and try to hit Control-C to get out of it? Okay, so that snarky message you got, that was, we did that by installing a sigint handler in your bomb. Okay, so when you type Control-C, that elicits a sigint. When that sigint is received, we printed this message and then eventually let you exit. Now, signals are another examples of concurrency. Now, we've seen concurrency earlier in the form of processes, right? Concurrent flows overlapping in time. Okay, logical flows overlapping in time, by definition, are concurrent. Now, with processes, because they have separate address spaces, those concurrent flows never interfere with each other. Right? So in some sense, processes are very easy to deal with, and we don't really have to worry. One process doesn't have to worry about being interfered with by another process. In fact, you have to go to great lengths to share things between processes. You have to use specific system calls in order to, say, share memory between two processes. Now, signals are another form of concurrency. This is the second time in this class that you've experienced concurrency. And so a signal is just a concurrent flow, it's just a logical flow. So a handler is just another logical flow that runs concurrently with your program. Right? So let's say we're executing a while loop in process A. Okay, and that while loop is executing. And then process A receives a signal which causes a transfer of control to this handler. This handler executes. So this is a concurrent flow that overlaps in time with the while loop in process A. Eventually, this handler returns, and we return back to process A. Now, one of the reasons signals are so tricky is because of this overlapping concurrent flow, this concurrency, because the signal handler runs in the same process as the main program. So it shares all the global variables of that program. Okay. So that signal handler is a function that you've declared, and it has access to all the state, all the global state in the program. Okay. And the existence of this shared global state can create real problems. Right? And we'll get into more details about some of those problems. So another way to look at these signal handlers as concurrent flows is using this context switch diagram. So suppose we're executing in process A, and now at some point a signal is delivered to process A. Now nothing happens, right? Just the pending bit gets set in process A at this point. Now at some point there's a transfer of control into the kernel, and the kernel decides to do a context switch from A to B, and now B gets to run for a while. There's another transfer of control to the kernel, and the kernel decides to schedule process A, and now right before it returns control to process A, it notices that the pending bit for this signal is set. So it causes process A to receive that signal. So that executes the handler code. When the handler returns, it returns for briefly to the kernel, which then transfers control back to the next instruction that the process was going to execute. Now handlers are also tricky because they can be interrupted by other handlers. So suppose we have our main program that catches a signal S, which causes a transfer of control to handler S. And then while handler S, oh, did you have a question? Oh, okay. While handler S is executing, the program catches signal T, which causes a transfer of control to the handler for T. And when that handler returns, it returns to the point to the instruction in handler S that was where it was interrupted, and then handler S continues its execution, and eventually it returns back to the point in the main program where it was interrupted. Now, signals that the kernel always blocks pending signals of the type currently being handled. Right? So a handler for a signal of type T can't be interrupted by the receipt of another signal of that same type. Okay, it can be, as I showed in the previous slide, it can be interrupted by a signal of another type, but not by a signal of the same type. So that's sort of an implicit form of blocking. But the kernel also provides a system call that allows you to explicitly block and unblock signals in the form of the sig procmask function. And then there's an associated, so this allows you to block and unblock a set of signals, and then there's some support functions that allow you to create those sets. So just think of these as bit vectors, and these functions will set and reset the bits in those bit vectors. So let's see how we can use sigprocmask to temporarily block and unblock a signal. So this is going to turn out to be very important for you when you working on your shells, which is your next lab assignment. Okay. So what we do, we'll use sig empty set to create an empty mask. So this is a mask with all zeros, okay, with no elements in the set. And then we're going to add a single element to this set, which is sig int. And now we have some code that we don't want to be interrupted by receipt of sig int. Okay. So we want to temporarily block the receipt of sig int signals. And we do it by calling sigprocmask with the command, say, I want to block the signals that are in the set specified by mask. And I'll assign so this will become my new mask. So this becomes the new blocked bit vector, okay, or the new signal mask, and it makes a copy of the old one and stores it at the address specified in the third argument. So at this point, after we return from sigprocmask, sigint signals are blocked and they won't be received. And then so we can execute this code knowing that we won't be interrupted by receipt of a sigint. And then we can restore the previous block set by using the sig setmask operation and passing in the previous mask that we saved up here when we initially blocked sigint. Okay, so signals and signal handling is a really tricky business. And there's sort of three things that make them so tricky and kind of nasty, really. One is that you have to be very careful to write handlers that are safe. Okay, so you can write signal handlers that are unsafe in the sense that they'll create a deadlock in your program. Okay. Or you can write signal handlers that'll corrupt a global data structure that's being modified by the main program. So I mean, imagine your main programming is updating some data structure like a linked list. And right in the middle of updating that data structure, when it's no longer consistent, the program gets interrupted by the receipt of a signal. And if that signal handler is updating that same data structure, reading that structure or modifying it, then it's going to encounter it in an inconsistent state, and you're in trouble. Okay. So the fact that it's easy to write signal handlers that are unsafe is one aspect that makes them tough to deal with. Another aspect is they have this funny semantics that signals aren't queued. And so if you're not really careful about this, it's very easy to use the receipt of signals to count events. And you can't do that. If signals were queued, you could use the receipt of a signal to count events in the system, but you can't do it because their signals aren't queued. And then a third aspect of signals which makes them tough is that they're not even portable across different versions of Linux. Okay. So if you use Solaris or some form of BSD, it's not necessarily the signal handling semantics aren't necessarily the same as they are in Linux. Okay, so we'll look at all three of these in a little more detail. And first, we'll start with writing safe handlers. So let me give you some guidelines for how to write safe handlers. And this is just a collection of sort of collected wisdom from various sources, but it covers a lot of aspects of signal handlers. So the first guideline is to keep your handlers as simple as possible. For example, the simplest possible handler I can think of just sets a global variable, and then it returns. Okay. And in fact, CERT, the CMU CERT provides guidelines for sort of compliant programs. And this is the only signal handler that they allow. This is the only compliant signal handler, one that just sets a global variable and then returns. Okay. Guideline number 1, call only functions in your handlers that have this property of async signal safety. Okay. And we'll look at this in a second, but I want to point out that printf, sprintf, malloc, exit, functions that are very common and commonly used are not safe. Okay. Guideline number 2 is to always save and restore error no on entry and exit. So error no is a global variable that's set whenever there's an error in a system level function. So you need to save and restore it on entry and exit so that it doesn't get overwritten if you're interrupted by another handler. Okay, if you're accessing any shared data structures inside a signal handler that are also accessed by your main routine, then you need to temporarily block signals while you access that data structure, both in the main routine and your signal handler. Right? And the reason for this is what I described earlier. If your main routine is updating that global data structure and then it gets interrupted and the signal handler is reading that data structure, it's going to find it in an inconsistent state and bad things will happen. Okay, you want to be sure to declare any global variables that are shared between signal handlers and the main routine as volatile. Okay, the volatile attribute will prevent the compiler from putting that value in a register. Okay. So if you declare a global variable as volatile, it will always be, reads and writes will always go to and from memory. Okay, so this is very important, right? You might, if you don't declare these global variables as volatile and the compiler chooses to put one of those in a register, then you may miss that variable being updated. So suppose your signal handler is setting a global variable. And now suppose your main routine is spinning, waiting for that global variable to get set. Well, if it's in a register, the write to that variable will just update the register, right? And so your main routine is in danger of spinning forever, not seeing the change. Right? Okay, so always use volatile so that they're not stored in registers. And then if you have a special kind of global called a flag, which by definition is a variable that's only read or written, not incremented or updated, it's just read or written. If you have a variable with that property, then you can declare it with this sig atomic t attribute. And if you do that, then the system guarantees that reads and writes to that variable will be atomic. So you don't have to, in other words, you don't have to protect accesses to these shared, to accesses or references to those global variables. Okay, and so by atomic, it means that the read or write of that flag will always happen in one uninterruptible step. Okay, one uninterruptible load or store in particular. Now in practice, on most systems, this sig atomic t is an int. Okay, so you can read or write an int with one instruction. Okay, so it's atomic. But if you want to be portable, you declare it with sig atomic t, and then it'll work on it'll work on all systems. Okay, we mentioned this property of async signal safety. Now, a function is safe to be used inside of a signal handler if it's either reentrant, okay, or if it can't be interrupted by signals. And a reentrant function, as we'll see when we study threads, is a function where all of the data that it accesses is on its own stack. Okay. So no global variables, no pointers to global variables. Everything's stored on the stack locally. Okay. So that means you can be, it's called reentrant because you can have multiple instances of that function, and they all have their own separate copies of all of the variables that they're using. Now, the POSIX standard guarantees 117 different functions to be async signal safe. These include underscore exit, write, wait, waitpid, sleep, kill. But unfortunately, there's some very popular functions that aren't on this list. Printf, sprintf, things that you really want to use. And in fact, write is the only output function that's async signal safe. So this is kind of a problem because, especially when you'd often like your signal handlers to output information, but you can't, if you want to really be pedantic and careful, you can't use printf. In fact, it's possible to write a program, and it's possible to write a program that does a tight loop of printfs in the main routine, and then a steady stream of interrupts which execute a handler which also does a printf. Okay. Now, the printf call has to acquire what's called a lock on the terminal. Okay, each printf inside that library function, it acquires a lock, which means only one instance of printf can write to the terminal at any point in time. If another function tries to acquire that lock, it has to wait until whatever function owns the lock releases it. Okay, so a lock is a way to get mutually exclusive access to shared resources. So if we have a tight loop in our main routine with executing printf, imagine what happens if one of those printfs acquires a lock on the terminal and then gets interrupted. Now, by the receipt of a signal. Now, within the signal handler, it calls another printf, and that printf tries to acquire that lock, and it blocks forever, because nothing's going to release that lock, because the main routine was interrupted by the handler. So you have what's called a classical condition called deadlock, which is we have a process waiting for an event that'll never occur. In this case, the printf in the signal handler is waiting for a lock to be released that'll never be released. So it's interesting. You can try this. It's not too hard to create this deadlock kind of situation. So to deal with this, I really didn't want to tell you guys that you couldn't have any output in your programs. And write's a very difficult thing to deal with. So I created a small little library called the Safe.io library. Consists of 3 routines, and they're available to you in the csapp.c file, which is distributed on the website. And it consists of 3 reentrant routines. SIO putS prints a string. PutL prints a long. And SIO error prints a message and then exits. Okay. So you can safely use, take my word for it, you can safely use this in your signal handlers. So if we were going to rewrite our SIGINT handler from the binary bomb, we could rewrite it like this, and now we have every function is async signal safe. All right, now signals are also tough because of this funky non-queuing semantics. And so it's really easy to make mistakes when you have an implicit assumption that the receipt of a signal can be used to count the occurrence of an event. So let's look at this. Let's look at this example program. We install a SIGCHILD handler. Okay, and this is actually this sort of, I want to close the loop. Remember, when we talked about our example shell, we're wondering how are we going to reap those background children? Well, we do it by installing a SIG-child handler like we're doing in this example. So here we have a program that installs this SIG-child handler, and then it creates n different child processes where each child sleeps for a little bit and exits. Okay. And then it spins until the C count variable becomes 0. The parent spins until the C count variable becomes 0. Now in our child handler, we have a global that's initialized to 0, C count. And then we're going to wait, so this child, when the child handler gets called, that means it's called because we received a SIG-child signal. Okay? So in our handler, we're going to reap that child by calling wait. And we're going to and then we'll decrement C count. Okay? So once all of the children have been reaped, C count will be 0, and then the parent can exit this while loop. Okay, now in this particular example, n was 5. But when we run this code, the handler only gets called twice. Okay, so the message handler reap child only gets executed twice, right? Which means the handler was only called twice. We created 5 children. We terminated 5 children, but we only reaped 2. Okay, so the problem is that we assumed that the receipt, that the execution of the child handler corresponded to the single receipt of a single SIG-child signal. Okay, when in reality, these signals aren't queued, right? We had, in reality, multiple SIG-child signals were delivered to that child, which kept overwriting that bit in the pending bit vector. And the delivery of those signals didn't cause any reaction in the process until that process was just about ready to be rescheduled. And only then was a signal received. But even though, like, say, 3 signals were delivered, only 1 was received. Okay. So you can't use events. In this case, we're using signals to count events, which in this case is the termination of a child. Okay, so the receipt of a signal, in this case, only indicates that at least 1 child terminated, right? Not 1 child terminated. All we can infer from the receipt of that signal is that at least 1 child has terminated. Okay, so to fix that, when we receive a SIG-child, we have to put the weight that's reaping our children, we have to put that in a loop. So we have to assume that the receipt of a SIG-child, if we get a SIG-child, there could be multiple terminated children that we have to reap. And so we put that in this loop, and we execute this loop until there's no more terminated children. In which case, wait will exit with an error code of -1 and an error no of eChild. So this isn't really an error. It just means there's no more terminated children. So we check as long as if our error no is not eChild, then we have an error. Otherwise, we terminated normally as we expected. Now, if we run this code, now we see that we reap all 5 children as we should. Okay, so the litany of problems with signals. First, it's easy to write handlers that aren't safe. Second, it's easy to get the semantics wrong. Third, they're often not even portable across different versions of Unix. So there's some older systems, I don't know if any, there's some earlier versions of Unix that after you catch a signal, it restores the default action. So you have to reinstall the handler every time a handler gets called, you have to reinstall that handler by calling signal inside the handler itself. We don't have to do that for Linux systems. On some systems, when you have so-called slow syscalls, for example, read, if you do a read system call, the kernel doesn't wait around for that data to arrive. It sends a request to the disk controller and then schedules another process. Right? So in a way that the read call is and then only when the data arrives and the interrupt comes in announcing that the data arrives, does that read call finish and then restore and return. So you can think of read as actually kind of broken up into two parts, right? So the functions like read, these kind of functions are called slow syscalls. And on some systems, if the process receives a signal before a slow system call has finished, the kernel will just abort that system call and return from that system call with an error. Okay. So from the user's point of view, you're doing a read call, and it returns with this e-enter signal, this e-enter error. You did nothing wrong. You just happen to have the bad luck of being interrupted by some signal. And so in your user code, you have to check for that. And if a slow system call like read is interrupted by signal, you have to redo it. So you have to put, which is really a pain, right? Because you have to put these read calls in a loop and keep looping until it succeeds. And finally, some systems don't block signals of the type being handled, right? So the solution for this is a replacement for signal. So the problem is with this signal syscall. And the solution is a newer syscall called SIGAction, which provides a mechanism, a replacement for signal, that provides a mechanism for portable and predictable signal handling. And so what I've done is created a wrapper called uppercase signal that takes the same arguments as the signal call, but inside it calls the SIGAction function to get portable signal handling. And so it's not really important to go into detail about this. The point is, in your code, you always want to call uppercase signal using the wrapper that I provided in csapp.c. And then if you do that, then you'll always block signals of the type being handled. The system will automatically restart slow syscalls that have been interrupted by signals. Okay, so fortunately there's an easy fix for this. Now let's finish up with, there's some interesting, I mentioned that signals are difficult because of the fact that they're concurrent flows. So I want to look at some sort of subtle issues that you can run into because of this concurrency. And I want to talk about how to identify those errors and how to fix them. So here's a program that, this is like a simple shell program that maintains a jobs list, right? So every time it creates a new child, it adds it to the jobs list. And every time that child terminates, it removes it from the jobs list, okay? So our simple shell, just in a loop, it just creates a child and then executes a program within that child. And then in the parent, it correctly blocks all of the signals temporarily while it adds the job to the job queue. And then it unblocks those signals. Okay, so this is correct in that it's protecting access to this shared job queue, because that job queue is also manipulated by the SIGChild handler. So when a child terminates and the parent receives the SIGChild, this handler runs, and this handler goes through and it reaps all of the children, the potentially terminated children, and then for each one, it deletes that job from the job queue. All right, so here's a classic case. We have two concurrent flows, our main routine and our signal handler. They're each accessing a shared data structure, in this case, the job queue. Okay. And they're correctly blocking signals while they update this job queue. But this program has a really subtle and nasty bug in it. Can you see what it is? What's the sequence of events that would cause this program to fail? Yes?
Is it possible it could finish and try to remove stuff from the queue before it tries to add it?
Exactly. That's exactly it. So is it possible that the child process could terminate before the parent has a chance to add that job to the queue? And the answer is yes. Right? You cannot make any assumptions about the execution ordering of the child in the process or about how long they run. Right? So it's very possible that the child can after the fork, control returns to the child instead of the parent, and then the child terminates before the parent ever has a chance to add that job to the job queue. So now, what's happened is that the child is deleting a job that hasn't been added to the job queue, right? And now when the parent finally gets around to running, it adds that job to the job queue, and that job will never be deleted, right? So this is the kind of subtle, nasty, horrible kind of bug that you run into when you're dealing with concurrency. Trying to keep track of all of these interleaving of events can just make your head explode, all right? Now, and it happens with any kind of concurrency where you have concurrent flows accessing shared resources, and signal handlers are no different. Now, we'll look at principled ways where we can deal with this kind of sharing when we study threads later on. But I just want to point this out to you and scare you a little bit. All right, so here's how we would fix that. What we have to do is somehow avoid the possibility of the child handler executing before the parent can add the corresponding job to the job queue. Now, we can't control whether the child executes first or the parent executes first, and we can't control how long the child runs, but we can control when the SIG-child handler runs because we can block signals. Okay? So what we'll do, we'll modify our program to, we'll use SIG procmask to block SIG-child signals before we create the child. Okay? So at this point, after this invocation of SIG-proc, SIG-child signals are blocked. Okay, then we create the child, and before we do our exec VE, since we don't know, that child may need to reap its children, right? We don't know if it, by default, children inherit the blocked bit vector of their parents. Okay, so when this child runs, after it returns from fork, at this point, right after the fork, SIG-child is blocked in the child as well. Right? So if we didn't do anything, and the child created children and tried to reap them with a SIG-child handler, that SIG-child handler wouldn't run. Right? So that would be a problem. So in the child, before we execute the program itself, we unblock SIG-child. And this was an example that I was alluding to last time of how it's useful sometimes to separate creating processes with executing programs. Right? So this allows us to get our signal mask set up the way we want it before we run our program in the child. So now, even if the child terminates early, the SIG-child handler won't run until after we've added the job to the job queue, because we don't unblock SIG-child until after the until after we call add job. Okay. Okay, now there's another, so this sort of scenario will be very relevant to you when you do your shell lab. Okay, and so you want to be careful not to make that mistake. Another thing that you're going to need to do in your shell lab. Now you remember in our simple shell example, we did the wait inside the main routine. So we waited for foreground jobs using wait. But now in a real shell, we're going to have our sigchild handler do all the waits, call all the waits. And so we can't put, the wait has to go in the sigchild handler, can't go in the main routine. Okay, so if we can't put a wait in the main routine, how are we going to detect that our foreground job is finished? Right? So somehow, so what we could do, we could define in the sigchild handler, when we reap the foreground job, right, we've created a foreground job. When we reap that foreground job, we could set this global flag, we could declare this process ID variable, PID, as a global flag, and then just assign the process ID of the foreground job. Okay, so in this is an example of a handler. All it does is sets a flag and then exits. And then in our main routine, okay, we want to block sigchild just like before, okay, to avoid that race condition between the parent and the child. And then we create the child. And then the parent, we set PID to 0. Okay, then we unblock sigchild, and then we wait for the sigchild handler to run and set PID to non-zero. Okay. Okay, everybody see that? I mean, so this is correct, right? But it's extremely wasteful, right? We're using valuable processor cycles in this tight spin loop, just executing over and over and over and over and over and over for who knows how long. Okay, so that's not a good solution. All right, so let's look at a couple other things we might consider, and that have been considered by generations of 213 students. So one thing you might think, well, I'll just instead of just putting a semicolon here, I'll pause. And then I'll wait for the sigchild handler to run, and then I'll go back up and I'll check PID again. Now you have to put this in a loop. It still has to be in a loop because we have other signal handlers in our program. We have a SIGINT handler. So it might be if we do the pause here and the SIGINT comes in and the SIGINT handler runs, that would cause us to exit the pause function and go back up. So we have to keep checking PID because we're not sure. We have to keep checking for the specific signal handler, sigchild handler, to run instead of other handlers that might run. But this is actually wrong because it has a race. Can you see what the race is? What's wrong with this? There's a good chance that this thing will block forever. Yes?
So, like, to get a signal, check PID or PID set, then the thing that, like, the PID runs, and then you have it in the signal?
Yeah, so the problem with this is like, so if the signal is received after PID is checked, but before the pause executes, okay, which is possible, right? It's unlikely, but it's possible. If that signal arrives here, then the handler will set PID to non-zero, and then we'll execute the pause, and the pause will be blocked forever waiting for a signal that will never arrive, right? Because the sigchild signal already came. Very subtle, right? So this code looks okay, it looks benign, but it's wrong. And your program would just hang forever. So we say, well, okay, that's no good. We could replace the pause with a sleep. So we could say, let's check PID, and then sleep for some predetermined amount of time, in this case 1 second, and then go back up and check PID again. So while this is correct, it's way too slow, right? We're asking the system to wait for a second, which is an eternity. And there's forms of sleep that are nanosecond where you can wait, instead of units of seconds, you can wait in units of nanoseconds. But what value do you use, right? If you choose a value that's too large, then you have this problem, this slowness problem. If you choose a sleep time that's too small, then you have the other problem, that it's inefficient. So the solution is to use sigsuspend, which is the last thing we're going to look at today. So sigsuspend is a function that takes a signal mask, and it's equivalent to an uninterruptible version of these 3 statements. So we block the signals that are specified in the signal mask, and then it's atomic in the sense that after these 2 statements can't be interrupted. They're always executed together. Okay, so we block these signals, and then we execute the pause. Okay. So there's no chance of a signal interrupting this program in between the sig proc mask and the pause. Okay, and then when a signal does come in and the execution of the handler causes pause to exit, then we set the mask back to what it was before. Okay. So the proper way then to wait for a signal is to use sigsuspend in the following way. So here's our program again. Before we create the child, we block sigchild, then we create the child, and now we're going to wait for the sigchild to be received. Now sigchild is still blocked. Okay, so there's no danger of the sigchild handler running. Okay, so we set that global variable to 0. And then while it's non-zero, we repeatedly call sigsuspend. And sigsuspend is using the previous mask that was set up here. So sigsuspend is using the mask where sigchild is unblocked. Okay, when we entered this first sig proc mask, sigchild was unblocked. So this allows, inside the sigsuspend, sigchild is unblocked. Okay, so it allows for the handler now to be received, or to be executed. Okay, so it does it safely because of the atomic nature of those first 2 instructions. So so it's possible that the implicit pause inside of sigchild could be interrupted by, say, another signal, like sigint. Okay, in which case we'd loop back up, we'd notice that PID was still 0, and we'd go back into sigsuspend with sigchild unblocked. Okay? So that makes sense to everybody? And now, so this is exactly the behavior we want. We're not wasting resources, but we've eliminated the race. Okay, so that's it for today. If you're interested, non-local jumps are this weird thing in C that allows a function to return to some other function that didn't call it. Okay. But it's described in your textbook and also in some additional slides here if you're interested.